Welcome everyone. This is a new NCT Data Science seminar, and we are really proud that we are back in the DKFZ Communication Center today. And this is our first live event for this year and hopefully for a long time now. So today we welcome our speaker. It's Uwe Korn from Quantco, and a warm welcome to you, and also to Gregor Köhler, who will do the introduction.
Right. Can you hear me all right? So welcome everybody. Excited today to have Uwe Korn as a speaker, who's hopefully going to tell us how we can build more efficient data pipelines. But before I hand over to Uwe, let me share some introductory words. So Uwe did his studies in Karlsruhe and Bristol before joining Blue Yonder as a data scientist. And at Blue Yonder, he worked on all kinds of things, from data pipelines to analysis, but also talent development, I heard, and sort of shaping the role of data engineer at the company, which I believe wasn't as present back then as it was today in the community. So Uwe and I actually had a brief overlap there at Blue Yonder. And this is where I sort of became aware of his work, not only at the company, but also all the impressive contributions he did to the open source community. And I really want to highlight them today here. So Uwe is a contributor, not only to Apache Parquet, but also to Arrow, to kind of well-known projects in the community, and also projects on which many others data science applications rely, really. So I think those are worth mentioning. And I guess over 11,000 stars of Apache Arrow and almost 3,000 forks on GitHub, they kind of speak for themselves. And Uwe is also a regular speaker at conferences. So I guess we can expect a nice talk today. So he's speaking often at Python-related conferences like PyData or PyCon. And I guess, like today, he often educates the community on sort of the latest developments in the projects he's working with. And after Blue Yonder, he joined Quantco in 2019. And I guess, among other things, he worked there on something we in the community often take for granted, which is sort of software packaging. And I can only speak from experience that as a user, you're happy that it works seamlessly, but you don't really know what sort of work goes into this whole thing. And I guess we kind of have to thank, among others, Uwe for it. So I believe this is where he kind of got in touch with also Condor and Condor Forge, because also since 2019, he's a core team member of the Condor Forge team. And I guess Condor Forge also needs no introduction. So I think it's important to knowing how we in the community sort of rely often on these amazing open source projects to, from time to time, think about that there's actual people sort of working on them. And if we as users often can only do what we do based on the work of people such as Uwe. So without further ado, please give a warm welcome to Uwe Korn.
Thank you for the nice introduction. Today I'm going to speak a bit about parallelizing data pipelines. Nothing packaging, but more about things we do in a daily work. And everyone who works with data pipeline, data in general has to think of how to write it, how to make it better, and how we can get there and have like speedy run so that we actually get down to the things we want to see at the end, what comes out of our research, what comes out of the things that we have gathered. There was already a short introduction about myself. I think the important credibility about me is I've worked a long time as a data engineer, so I've built a lot of these data pipelines, spent a lot of work on tuning them. For me, I've been working in industry, so I've spent most of my time on table data, like relational databases. Try to make the talk a bit more general because that's what we all have in industry. But like if you're outside of the industry, you typically have more than just tables and CSV files. So in general, I want to talk here about parallelizing any kind of data pipeline, which follows still a general pattern. Because if you think of a data pipeline, maybe even a water pipeline like this one, there's something that goes in at the beginning. It's typically a collection of files that you have gathered somewhere. Maybe it's already in some kind of database, but you have your input data that you want to process, and you want to like augment it with some things that you have gathered. You have maybe also like a model that gives you more information as part of that. And at the end, you want to do something that draws value from the data. The value can be trained a model, you build a report, or you found out something else. But at the end, you've pulled something out of the data, which aggregates the like important thing that's in there. Parallelizing a data pipeline is important because of several steps. Most important one, it's running faster, so you get your results just faster. That maybe means if you have to wait a long time for your results, your coffee break will be shorter, but at least you will be able to get multiple results in a day, or between in the morning you get like not only one run, but like 20 or so. Otherwise, simple laptops we get today, they have at least 4 cores. Some of them have even a lot more. And if you don't parallelize, you just using one of them, which is just a waste of your resources. But most likely you have access to some kind of cluster, and you actually want to use it and draw some value from that and just get the things you have much more faster. And finally, with a large data set, kind of often your local machine doesn't sufficient to just put data in there and process it. It's just too small. So with parallelizing and putting it out to several machines, you actually just get enabled to do your analysis on the full data set. And for that, you also need parallelization. You can use some of these patterns to talk to things that are related to what are defined as a data pipeline. If it's like a sum of independent tasks with like similar workloads, where you maybe don't draw anything at the end as a value, but maybe use for preparation of your data. Like the patterns here apply too. But one common misconception I see quite often is when you gather data, like in the case of web scraping, having more CPUs won't help you because you're not actually processing things, you're waiting for things. And that's a thing where you can use asynchronous programming, which is the thing of its own. And if you're just waiting for things, don't just use the whole cluster, because if the cluster will be waiting for you in parallel on these things, you can solve it differently. In general, the talk today, I'm trying to give you general patterns for data pipelines so that you can apply to any technology, any kind of data, because there's like, if you structure a pipeline correctly, you can do it more efficiently. I will shortly talk about technologies you can use for parallelizing. There are a lot of them out there. I'm just going into a few of them and why I picked a selection of them, one specific one, and hopefully can use that reasoning for selecting a technology out of the tools that you're using. And at the end, it's a technical talk, so I want to give some code samples, really small, but applying the patterns I mentioned in the talk and show them how they end up in parallelization. In the beginning, it's independent of technology, the theory. So we start a pipeline with some kind of data. I'm differentiating here between tabular data coming out of CSV files or Excel files, which you can put into a SQL database. And at the beginning of a data pipeline, I would strongly recommend to put it into a SQL database, because SQL is a good language which helps you to just peek into the data, do simple operations, maybe even join things together. That's where it's perfect. Later on, you maybe don't need these capabilities anymore, and using a database is just a bit of overhead. Then use a set of files on an optimized format. I'm someone who's working in the Parquet project, so I'm also recommending if you have table data stored in Parquet files, that's most efficient. But do you use multiple files? That will be of a big benefit. Don't just put your whole data set into a single file if it's quite large. And if you don't have like tabular data, but you have like a set of unstructured JSONs, images, or so on, You can put that in a database, something called a document store, which deals with this non-table data. But I would really recommend to invest in a directory structure where you put in your data. Directory structures are simple, and it should be a structure of directories, not just one directory with all your data in it, because then if you have a good structure, you can actually make use of that in parallelization, selecting subsets of your data, finding out where some specific data point lies, instead of going through a large list of files, but you can narrow it down by maybe saying, okay, if you go into this subfolder structure, there's something specific, look into that. Maybe start from that, only a small run. And that actually takes us to the first point. As with most things in programming, the important thing if you develop something is your iteration speed. The faster you get feedback, whether your code works, whether your code produces reasonable results, or whether it's just running and how fast it's running, find out that you can start and develop really fast. And developing really fast is either you have a really good set of unit tests, which is quite unlikely if you start out with a data pipeline because you're most likely not sure what actually you want to have from the pipeline. In later stage, when you know your pipeline is working, you can write tests to make sure that if you change something, it won't break again. And you also already are possibly aware of the edge cases. If you're starting new out, you're probably not aware of the edge cases of your data. So writing tests that check the edge cases is really a hard thing. And that's why I suggest to have some subsets of your data sampled ready before you start developing. The first one, it should be a set that runs really fast. Preferably, I would say it runs in 10 seconds, but typically you have some overhead. You load some configurations on, so 10 seconds is maybe the latency you have when you run your pipeline always. So find something that runs in a minute. Don't have something that runs on a single sample because that probably won't trigger any reasonable code paths. It won't give you any output, but you can already do some thumbnail checking whether it's actually okay what it does. But get something that's small, that's fast. That's a thing you're going to use in development. If you change your code, you run it, you see whether it works, what it produces, whether everything's coherent. And then choose something that's of sufficient size so that you can see whether the output produces anything reasonable. If you do any statistical modeling, machine learning or so, if you use a small 1-minute data set, it's probably not enough statistics to give you a good output whether something performs well or not. That's why you should have something that gives you something with sufficient results. So you can see, okay, the code runs, it's fine, and the results are also fine, so and it makes sense. So there's not some programming error that's not detected by code calls, but just by maybe using the wrong functions on your data. And finally, if you have your full data set, you should chunk it into reasonable equal sizes, called chunks or partitions in this talk, where when you parallelize the workload, one maybe CPU will run one of these partitions. It's helpful to have like one of them stand out for you, explicitly Mac. So when you run and develop a pipeline, that you have a sample which gives you a reasonable performance. So if you want to make it faster, you don't have to run the full data set, but you maybe want to know what's slow in my data set, then you can use this one partition, and you know that's exactly what one part of my data set will need in computation time, and I can check if my things I do, if they are really fast, because sometimes performance optimizations, they're faster if you use a small sample, but if you go to the bigger sample, it's something else that's making the code slow. And another thing is you do a lot of things in your pipeline. And as part of the pipeline, there are some steps where you have workload, where each workload in the partition is fully independent of what's done in other partitions. That's called embarrassing parallel, because you can't just run them all at the same time. If you don't do these things in parallel, it's going to be embarrassing. That's where the name is coming from. But hopefully you can reorder some steps in your pipeline, because if you put like this parallel part, all of what you have together at one point, you can pack it better together if you later run the task and have less amount of time where you're waiting, where some parts of the pipeline need to exchange information with another part. That comes just down to packing all the workloads on your CPUs together. If you split the embarrassing parallel part into several sections where you have to wait in between, you will just accumulate random points in your pipeline where you have to wait, and resource utilization will be less good. And because everything is independent, this is the task where it scales best, where you will be able to use all your resources if you have enough data. So and it will be perfectly used. CPUs will be fully working, and it's because there's no communication, it's really simple to parallelize. To get resort your pipeline to have a long part that's parallel and independent, what you can put at the beginning is typically you have some steps where you clean your data, where you normalize your data. For that, you need to communicate like minimum, maximum, and so on. And that's the thing, computing these global minima, maxima, put them at the beginning. There's this thing where you need to communicate between all workloads, but there's just one point in time where you need to communicate, and then applying these filters is a step you can do afterwards. If you have data sets of equal size and you want to join them together, also do that at the beginning, because at the beginning, if you have data in a SQL database, for example, it's really good at joining big data sets together, but then the point of pulling it out is something that's really costly. If you have to pull something out, push it in again, and out again, that's a lot of overhead. So just push all these operations in the beginning. It might mean that some of the operations you would naturally do, because some filterings you would do them later, because there's an intermediate step giving you more results. Maybe you can reorder and put it there. That's going to get a big amount of speed up, even though if you run it on a single partition, it doesn't make any difference. But if you look at the whole set where there's communication between workloads, it will make a lot of difference. In the middle, that's hopefully a part of your pipeline where you can do things that are independent. If you put all these global finding minima maxima out to the beginning, sometimes it's even you finding out what are all the valid values because you're doing one hot encoding. That's a point where you can apply it to the data, do some transformations. Sometimes they run on a single sample. Sometimes you need a set of samples because you're looking on a data set where you have an observation and you will see it over the timeline of over a year, where you have monthly checkpoints. Make sure to have all these observations, if they're a small grouping, in a single partition. Because then even if you need to communicate or information between observations, if they are in a single partition, there's nothing like the workload you have, it doesn't really need to communicate, it's just in there. So it makes it fast. This is the part where you want to maximize, the longer it is, the better you can parallelize. It's not always easy to have this really long, but this is the point where it gives you maximum utilization. At the end, there will also be some communication between the workloads, because if you want to draw some value, and if it's only transformation of your data, then this may not be happening. But if you want to draw value, you need to combine all the things you have. So there is always some point where you pull everything together and want to get results. If it's a simple report, that's a point where you possibly sum up all the values you have gathered or derived, and you aggregate things together. Important thing here is what hopefully the tool you're using also provides for you is to use a tree aggregation to make sure that if you have multiple machines, that you first aggregate the results that are coming from this one machine before sending it to a central point, and not that immediately every workload is sending their results to a central point. This is also the less communication or the less communication over network will make more performance. If you have a machine learning model at the end, this will also iterate several times over the whole data set, need to exchange things. The libraries of machine learning models nowadays, they all come with a distributed algorithm, with a library that does that for you. The library is something different you will use to reprocess the data. So the important thing here is that you have a good connector between the library you're using to make a distributed workload and the library for your machine learning model, and that there is a handover where you hand over the data, possibly without even copying it. But importantly about it is that it doesn't move from one place to another place, but just these things should run next to each other, do a data handover, and then the machine learning model library takes over. Yeah, I've been stressing a bit here about minimizing communication. Communication is the one thing that brings things to a halt, because when you communicate, your CPUs don't work, your GPUs don't make any work, and even though if you communicate inside one machine, that means some parts of your machine has to wait for another. That's not so good CPU utilization, but if you have to communicate over a network, and even though if it's a really fast cluster interconnect network, it will be 100 times, 1,000 times slower than if you communicate anything in your machine. So this will really stop things. It's necessary, without that, you couldn't make aggregate results, but just be careful when you do it. Be careful that it only happens like in certain points. And if you have to do it for multiple like algorithms, maybe find a way to combine that. Another thing is, if you go to a cluster, or if you just use many algorithms, many CPUs, it's going to likely be a failure of your code. Sometimes it's an issue with the network, sometimes it's just because one partition of your data has some kind of error in its data you didn't expect if you just ran on a small sample before. And it's annoying, because some analysis, I know, can take 1 or 2 weeks. If something breaks down then, running again for another week will lead to a lot of delay. So the first thing is, if there's a failure and it's because of network, maybe the library you're using supports just restarting the task. But that's also meaning you need to write your task so that it can run twice. So it should only depend on what you put as an input to determine the output. If you're writing to some file and reading it again, and it's like writing to the same file and reading, this is some, for example, thing which is a side effect and which can then change the results if you run this one partition twice. So you need to be really careful that this doesn't happen. And also, if it goes to a failure, try to minimize what has to run twice. Maybe have some logic that does some checkpointing of your data to disk. So you know, okay, if I reach this side, this position from a pipeline, I'm just going to store my intermediate state to disk, maybe add some meta information to it so that when I restart a pipeline, I know, okay, I went this far and I can continue here. So that if my pipeline that runs a week fails after 3 days, I don't have to rerun the first 3 days, but I can start up from then. And maybe okay, it failed because of a programming error, because I didn't think of this one edge case. Then you can just handle that and run from there. And also, if you run into programming errors and it's an issue, make it so that you can just run the pipeline for this one partition, because this allows you to debug, find out what's going wrong, what's the issue, and you can see then why it breaks without having to guess and then run the full thing again. Another side effect is if you store your intermediate results to disk, you can also save on memory, because you can just store a result, save it to disk, and maybe do some other part you also need, or maybe you have more workloads than CPU. And if you store it to disk and keep it out of your memory, your peak memory utilization will be smaller. And that helps if you have like intermediate steps that just have a short memory peak, which would otherwise exceed the RAM of your machine, and it allows you to run it in a smaller system and being resilient at the same time. Checkpointing, you could also say it's kind of caching, meaning, okay, if I rerun it, I have my intermediate results cached. They help you. In this case, it fails. They help you if you want to debug and run a single partition. Maybe you also have, not only does it fail, but there's maybe one partition that takes 5-10 times longer than all the other partitions. That could also be something where either there's an error or something kind of weird with your data. This gives you the chance to just peek into it, understand what's going wrong. For these intermediate partitions, it's important to use really efficient formats, because if data is in RAM, handing it over to the next task is really fast. If you save it to disk, this is going to give you some overhead. It's also the important thing that it might change the types you have in your data, because in RAM you can use exactly what you want. If you save it to disk, the data format will limit you in what data types are supported. Sometimes it's just changes the values or the width of floats or so. But use an efficient binary format. Table data could be Parquet. If you have matrices, there's SAR. And store them on a distributed file system. If you have a cluster, or if you're working in the cloud, there's some things like object storage, which is like a distributed file system, but with maybe less features. Because in a distributed setting, all machines can fail, and if they don't come up again, the intermediate results on these machines will be lost. And also, if you want to debug a single one, just getting sometimes access to this one dedicated machine isn't possible, because it's part of a cluster schedule that only allows you to connect to that machine. Speaking of having one partition in your data taking longer than a lot of others, this can often come from the fact that you didn't your data is grouped by natural grouping, but the natural grouping does lead to uneven groups. And there's a common technique how you can even out all these groups is if you use a hash function. And a hash function in computer science, it has a general pattern. It takes in some input. It gives you some output that is connected to the input data, but it's enormously different if you do slight modifications to the data. But the output, given the input, it's normally a uniform distribution. So if you use from that output maybe the first 3 bits or so, you get an even distribution on 8 evenly sized partitions, or with a statistical variance, but it gives you an even distribution, even though your natural grouping wouldn't be an even distribution. And in some cases, it's useful to have a small pipeline that takes your data, and it just does a repartitioning so that it takes all the data, uses 4 relevant keys that determine of the observations that should be together, and then puts it into folders that are named after the first 3 bits. And then you can start from there on and know, okay, I've repartitioned my data, everything is even partitioned, and so my utilization will be good again, and not having to wait for the single one partition that's so huge. You can use something like cryptographic hash functions, because if you search for a hash function, you would typically find things that is used to really verify that contents have not changed. These are slow. If you only are concerned about the aspect of even data distribution, things like XX hash are the ones you can use because they can work on really large amounts of data and really fast. That's typically in this use case the much better version. Not so easily supported in databases, but if you're working outside of the database, typically you will find XX hash being available there. Also, general thing with coding is a bit more complicated here because we're working about distributed software. Is profile what takes long. In a good case, you have a library that helps you to distribute your workloads among machines that also brings some tooling with you to collect where your time is spent. I'm typically using flame graphs for that. Flame graphs is a visualization where you check always the stack traces of your code and turn them on top and just order them alphabetically. This shows you a bit where the hotspots in your code are. This removes the order component, but the width of each horizontal bar is the time overall is spent in the cluster. And in this workload, I would look into the middle part because it's 80% of the time over the whole workload over all machines. And I know, okay, this is where the majority of my work is spent. I'm looking at the distributed profiling. If every workload is equal, if it's not equal, I will look at a single partition. But profiling will give you a good picture into what works. And quite often tools come with a statistical profiler. That's one thing that doesn't give you 100% accurate results, but because of statistics, it's giving you really close results to what actually the work is spent on. And it has a real benefit. It doesn't add anything to your runtime. So you can run it while you're working with it. It will maybe have 0.01% increase or so. But for you afterwards knowing, okay, this is where my time is spent. This is maybe the point of code where I can maybe spend more time in optimizing so I get faster results. Is really useful. It's also useful because you don't have to think of whether you add it or not in the start. Because if you realize your pipeline is slower, you will have the results at the end. Normally, you might only realize at the end it's taking too long. And you can peek into that while it's running. So you know, okay, currently all the things are running in here. And it shouldn't be there. So something's wrong with my pipeline. Maybe I stop it. Maybe I just analyze what's going on. Going a bit further, writing data pipelines is hard, but writing software distributed workload is really hard. So the important thing is think of the software foundation you're going to be using to distribute your workload. And depending on your workload, depending on your ecosystem you're working on, it will be a totally different choice of technologies. It also often depends on what actually people are there in your surroundings which have knowledge of technology, which you can use and get help from them. In my space, where I'm processing a large amount of data, which typically a tabular, I have to choose typically between these different technologies. like often the hype ones. Running things on a single machine. Mostly I can just use what my programming language has built in, so I don't need anything on top. A lot of in news is always Spark, because that's what the really big boys use for really large computations. It does a lot of optimizations for you. It does make things a lot faster if you put in the right workloads. It also needs like people that can maintain it, because it's a bit more complicated to set up. There's Apache Beam, which gives you access to a lot of different technologies. It comes with an overhead because it's a layer on top of things like Spark or something cloud providers provide, but it's maybe a useful thing to use if you're okay with your workload maybe running only half as fast as it could, but it just can run anywhere if you're switching between cloud providers. My preferred one I'm actually using is Dask. It's a Python library that helps you distribute your workload either on a single machine or on multiple machines. And it doesn't have like these fancy optimizations feature as Spark, but it's easy to set up. And up and coming now, especially in the deep learning area, is Ray, which has a similar approach as Dask, and that it's quite simple, but it's more actor-based. So if you like working on deep neural networks, it gives you a much better programming model for those. But as I said before, I like Dask. The main choice of it is it's simple for me as a user, because it's simple to start up, and I can choose whether I want to parallelize things on my machine or on a whole cluster by switching off a single line. It has these tools like the profiler I've shown you before, and I will show you some more pictures of it built in, so I don't have to set up any additional monitoring systems. But for me, the actually important features, which is like one of the main things Spark is advertising with them, is Spark has this enormous compiler that can take everything I do optimizations on top, do combining of all stages and so on. Dask explicitly doesn't have that. That brings, like, if you have big data transformation workloads of petabytes, you would have to do many manual things on your own. But in my case, which I often come across, is I don't have that much benefits of these whole stage optimizations. They add some latency to my code. If something goes wrong, I have to understand what's going wrong. And if I have a whole stage optimization compiler or something between, it's another component I have to understand, which doesn't give me direct access to what I have been coding. And just because I have quite good knowledge of the algorithms I'm using, I see my code, and it's much easier for me to go from the code I have to understand where the failure is coming from. So I actually don't want to have something that has these tools built in. That's why I stick with Dask. As I said, depending on where you're in your ecosystem sitting, something else might be useful, but for me, it's just stick to the simple one, which you can understand, because the annoying thing is if something goes wrong, you will be sitting there, will be annoyed, and you will be much happier if you find out what actually has went wrong. And finally, we've talked about what patterns to apply. So I want to just show a small example how these can be used. It's actually, I think, only like 10 lines of Python code, but it already is a good explanation of what these things are about. In my case, the beauty of Dask is I can do a Python call and spin up a local cluster on my machine. In this case, there is a Python class called local cluster that spins up on my machine. I'm in Python. Python has this limitation that a lot of code only runs, like one process can only run stuff one at a time. Some scientific code does this more, but you need to know before whether your code can do. That's why I'm setting this magic variable threads per worker to 1. And then I'm connecting with a client to my cluster. If you would have a big distributed cluster, you would put your cluster schedule here as an endpoint. In my case, it's just locally on my laptop. And then I connect to it and I can work with it. As the next thing, my data set of choice for demonstrating pipelines is always the New York taxi trip data set, because that's one of the few publicly available data sets with a huge amount of data. Normally, if it's big, you don't get access to it. So this is the one I'm happily using. Because I'm doing a small demo, I've split it up. You normally get data on a per monthly basis. I've split it up for the demo to a daily basis, because daily trips kind of equal. Like there's less trips on the weekend than on a weekday, but it gives us okay workloads. And already the library for me, what it does is it uses every file is going to be one workload that the library can parallelize. So we will have 31 independent workloads where we can work on. Data that comes in is messy. So at the beginning, there is a data cleaning step where we need to find out certain things. In this case, I'm just getting rid of some weird trips that are either extremely expensive or extremely far away. It doesn't make sense if you're just looking at taxi data that should only be in New York. So I'm just doing some basic outlier correction in the sense that I'm collecting the means and standard deviations of 2 columns. This means I have communication in my data set. So I'm specifying in the first section, hey, this is the things I want to know from my data set. Mean and standard deviation are actually really good ones because for each of them there exist algorithms so that you only need to go once over the data. So if you specify them, one pass over your whole data and sending it to a central worker which can aggregate these intermediate results will be sufficient. Then in the second section, I'm sending it in the client compute. I'm sending it to my cluster and actually computing it. Because I'm sending both at the same time, I can limit it to a single network communication or communication at all and not have this twice. This actually makes quite a difference if you put it separately or run it at the same time. I think it's just doubling the runtime because a single pass over the data doesn't cost anything compared to the time it costs that one instance ships a small tiny bit of information to another one. So this is one of the important tricks I mentioned, put it really into one step, minimize the point where you have to communicate that. And then I can put it into a query which filters my data. This is actually not immediately executed, but as long as I have things that are independent workloads, the library in this case knows that and just adds that on top as its computation and will only run it if you request it. So if we look at some visualization, what happens here, the query part, we will not see that. What we're seeing here is gray boxes, which tell us, okay, we're loading data into RAM to work on it. Then we have some small boxes, which are either blue or yellow, which are used to go over the data, calculate the intermediate means and standard deviations. And the red boxes are the annoying ones, which we don't want to see at all, but we have to see. This is where each of these workloads sends some information to another workload so they can exchange the values to compute the standard deviations and means. And that's the point where you also see where a lot of white area is, where you're not using your cluster as you could, and before that you're using it perfectly. Afterwards comes the good part, where we can work on each observation independently. We've just had this filtering query on top, and we're going to evaluate that. And also, one simple feature here is if you extracted the time of day into single components, you can put it into a machine learning model, and then you get better results. But extracting the time of day into its components is something you can do for each observation. So that's fully independent. And you then also strip out your data into X and Y so you can pass it to a model. In this case, it's not the best machine learning model approach because there are also columns which you can just add up to the fair price, but it's just an example how it works. And then at the end, you can pass it to a library. My go-to library is like GBM for distributed learning. Any other library will also have some kind of distributed library. But in this case, the important thing for me, it has an adapter so it can take datasets from Dask. At this point, when I call the fit function, it's maybe using Dask under the hood. I have no idea. For me, the important thing is it takes the data points and it doesn't move them to different machines. But it optimizes so that it looks at it, calculates the values it needs to communicate, and then does parallel work again. You can see that if we look at what's happening. You see in the beginning the yellow and green boxes. Partly of that is the filtering, partly of that is extracting the data components. Then you see a small amount of red, where LightGBM actually communicates some statistics about the columns. And then comes one standalone gray box. That's where LightGBM does a lot of computations on these intermediate statistics to find out, okay, what things do I need to compute into individual components? And afterwards, everything is running fully loaded again in parallel, because LightGBM is an algorithm that can, depending on how you distribute it, run also perfectly parallel. But the important thing is here, It's small red boxes, meaning there's only a tiny bit of information exchanged, and it's not that my whole data is rescheduled over the cluster and would maybe have to wait a long time. If there only was one point in time where I would send my whole data from one worker to another worker, this would dominate the whole workload here because it's actually one of the most costly operations. Yeah, I have the small sample. It's like 10 lines of code, but you still can look it up online. Probably the URL is the same length as the code. But that hopefully showed you like some patterns how you could approach the parallelization of data pipelines, which are hopefully applicable to many problem solutions we have to work in. Yeah, that's it from my side. Happy to take questions.